I am going to use the flow through an earth dam here to demonstrate procedures, features, and technique. This will be the flow through a homogeneous dam to start with, and then later on we will add a core to the analysis. The reason we select this example because it is a classic textbook case. Almost every introductory soil mechanics textbook or book on flow, seepage flow, has an example of flow through a homogeneous embankment. So everybody should have a very good mental image of the expected solution, and one of the elements of good modeling is to have some kind of a mental picture of what the solution should look like before we get started. Conceptualizing the problem is essential and necessary for judging the result. I will make a few more comments about this in a couple of slides, but we will start then with the first element or component of a finite element analysis, and that is geometry. We're going to open a file SEEP 01 or SEP 01, and what we want to do here is to illustrate how to draw regions and how to do some meshing. Now, to those of you who were part of the Slope W session, you already know how to draw regions, but let's go through the process once again about how to define regions in SEEP W and then to look at some meshing controls. So let us go to GeoStudio then and open this file. Say File, Open, SEP01. And we have only one analysis in this file here. And in actual fact, we haven't analyzed anything in this file. We have simply provided you with a sketch of the drawing, and it's always useful, in my view, to sketch the problem before you start making any definitions regarding the actual analysis of the domain. I believe it helps you plan the analysis. So in this particular case, we should have on Snap to Grid, and we can say Draw Regions. And let's draw one region that represents the upstream shell of the dam. And when I click back to where I started, the region represented by a polygon closes, and notice that I have a list, Draw Regions, I'll go to the next region to illustrate what I was going to talk about. In this particular case, I will go counterclockwise on the region that represents the downstream shell of the dam. I'm sorry, I clicked on the wrong command. We can click on the Undo button and say Draw Regions. And I want to draw a region that represents the downstream shell. And if I right mouse click, it closes the polygon to create a region that is made out of points 4, 5, and 6. Then I will draw a region that represents the core of the dam. We will not include the core at first, but later on we want to include a core, and so we will draw a region for the core now, but assign it the same material as the shells. So drawing regions is very straightforward in SEEP-W, as in all GeoStudio products. It is always the same. A region is simply a closed polygon, and as you will see in a minute, we can assign properties to regions. Now we don't need the snap to grid anymore, and I want to illustrate meshing at this stage. But in order for me to illustrate meshing, I have to assign material to these regions. And so I'm going to jump ahead of myself here a bit and say key in materials. And I'm simply going to select a material number 1. The name here doesn't matter. And I'm simply going to say saturated only. And I'm going to make the conductivity 1. Just because I want a material attached to the regions, the material properties are irrelevant at this stage. Now I can say draw materials, and notice my cursor turns into a small square when I'm over a region, and I can now assign this material to these various regions. And if we had this view mesh on, the mesh comes on by default automatically. Let's zoom in here a little bit. Initially you noticed that there were some labels on the meshing. We can say view preferences, we can say point labels and material boundaries and mesh labels. And the mesh labels, you will see that you can see a number of each element, and you can see the numbers of the nodes in light gray. Now generally it is the intent in GeoStudio 2007 that it is not all important for you to know the element numbers and the node numbers. So usually the mesh labels are turned off. We also don't often need to see the actual mesh itself, but it is useful to have a look at the mesh prior to starting to applying boundary conditions and so forth. Now this is a default mesh. It is actually quite an acceptable mesh for this particular case, but to illustrate that you do have control over the mesh, we go to the command called draw mesh properties. And right off the bat here, you will notice at the top we have a global element size of approximately 1 meter. This is the coarsest control on the mesh. It says that give me a mesh where all elements are approximately 1 meter by 1 meter. They're not exactly 1 meter by 1 meter, but they're not far off. We can change this control and say give me a mesh of 1/2 meter by 1/2 meter, and when you hit the enter button, then it completely remeshes it at a much finer mesh. So this is the highest level of control, or if we said 2 meters, then of course we get a very, very coarse mesh. Let us go back to the default of 1 meter. And now when this dialog box is open, we could say, well, I would like a finer mesh in the core area. And there are several ways to control the mesh. We could say, let us make the mesh 2 times as fine in the core as in the shell. We can select ratio of default size. So the ratio would be 0.5. And notice now that I have a much finer mesh in the core area than I do in the shell areas. This is one way to refine the mesh. Let's undo this refinement, go back to draw mesh properties. We can also click on a line, and we say on this particular line give me a certain number of divisions, and let us say 25 divisions, for example. and so we get a refinement along the line. So we can refine along a line, we can refine in a particular region, and if you do too much refinement, sometimes it's difficult to know what has been done, and so we have a special button here that says remove all constraints. And you will find that when you first start using SEEP-W and doing finite element analysis, you will have a tendency to want to make the mesh quite fine in certain areas, and you will have lots of controls and constraints on the mesh, and it gets confusing which constraint is doing what to the mesh. And so the button remove all constraints is quite useful. I would recommend to you that you start with the default mesh, draw mesh properties, approximate global element size. And if you could try, for example, as we already did, say 0.5 meter, then hit the enter key, you notice that we immediately have way more elements, nodes. Now we have 996. We have 996 elements when they are 0.5 meter by 0.5 meter. When they are 1 meter by 1 meter, then we only have 253 elements. So once again, the tendency is to start with a very large number of nodes and elements. I would encourage you to avoid the urge and not make your elements too small and have too many elements. As a very, very broad rule, if you are looking at your drawing at 100%, you should be able to visually see all the elements. If you have so many elements that they turn into a black blotch, then I would suggest you have too many elements and too much mesh refinement. There is no theoretical basis for this recommendation, but with all the years of experience with doing SEEP-W and finite element analysis, it is a very broad general rule that I like to follow. So once again, when you are zooming in at 100%, the true scale, then you should be able to see all the elements. And this brings up a point: the scale should be the same in the vertical and horizontal directions. If you are at 100% and you cannot see the elements, and it simply turns into a solid black area, then I would suggest to you that you have way too many elements and nodes. So there is a very rough guideline for you in what is an appropriate mesh. And once again, to re-emphasize, the urgency when you start is to make your mesh too fine and have too many elements. Consequently, you get too much data, and it takes too long to analyze, and it is much, much more difficult to view the results. So, as we noted earlier, let us try and keep the geometry fairly simple to start with, and that's also true for the mesh. Try and keep the mesh fairly simple to start with. Now, there are other mesh controls which I will very briefly highlight. Draw mesh properties. We could, for example, have just triangles, or we could have just quadrilaterals, but the default is quads and triangles. This is the most recent preferred approach, is to use predominantly quads with some triangles. Now, if you have some specific reason to just use triangles, that is okay, but I think the best and more appropriate solutions arise when you use predominantly quads and with the odd triangle that are necessary to fit in this pattern within a particular region. There are other controls like secondary nodes, but I won't spend any time on that here. It is a very brief introduction in how to do some meshing. To repeat again and give you some of our recommendations, we strongly suggest you keep the geometry as simple as possible. Generally, complexity does not mean a more accurate solution. Secondly, we suggest you include only components essential to the understanding of the problem. Notice that in our particular case here that we were just working on, we did not include this under tow drain here. The tow drain does nothing toward dissipating the potential energy, therefore it is not necessary to include it. Now later on in the SEEP session we will demonstrate how we can include it, but it doesn't make any difference on the results. So here's an example of not including a feature if it does not add to the solution. And lastly, unnecessary complexity can lead to uninterpretable results. And once again, on the workshop CD, there is a folder called Papers of Interest. And in this folder, there are 2 papers on modeling methodology. I would urge you to read these papers. They are quite short. It doesn't take long to read them. And in these papers, we talk about appropriate levels of complexity in numerical modeling. I've already alluded to this, and you will notice in those 2 papers in the folder, Papers of Interest, that we talk about appropriate numerical modeling involves conceptualization. We have to be able to conceptualize the problem in order to do an appropriate numerical analysis. And very briefly, it means that we have to have some idea of what the solution should look like before we start the numerical modeling. To illustrate what we mean by conceptualization, we can look at the flow through this homogeneous dam. We already know that in all likelihood that the line of zero pressure will start at the full supply of the reservoir, and it will be perpendicular when it comes into the ground, and then it will take some shape we expect like this, and we know this from our study and introduction to SEEP-W analysis. Now, very briefly, I could draw a second flow line here, and it would go something like this. And I know that my finite element, I'm supposed to have approximate squares, and so I could draw an equipotential line here, perhaps another equipotential line here, another one here, and so that I'm getting approximately squares. 1, 2, 3, 4, 5, 6, 7, 8. And so that is an extremely crude flow net, but nonetheless it's reasonable, and we can even make an estimate of the flow quantity. So first of all, from my SEEP result, I should see what a flow line or a line of zero pressure that looks somewhat like this. My equipotential lines should be perpendicular to a flow line. That's what I should expect. And the total amount of flow through this structure I could estimate from this equation, where there's the number of flow lines divided by the number of equipotential drops. Let's say that K is equal to 1 times 10 to the minus 5 meters per second. The total head loss, delta H, is equal to 8 meters. The number of flow lines is 2. NF is equal to 2. And the number of equipotential drops is 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say approximately 8 for easy figuring. E is equal to 8. And so Q is equal to 2 divided by 8 times 1 times 10 to the minus 5 times an 8-meter drop, so the 8 cancels out. So Q from the SEEP-W analysis should be somewhere in the neighborhood of 2 times 10 to the minus 5 meters cubed per second. This is just a very rough illustration of what we mean by conceptualization. It is incredibly important in numerical modeling that you are able to have some mental picture of what the solution should look like before you start the finite element analysis. If you cannot conceptualize what the solution might look like, then it is very, very difficult to interpret the results. So once again, not to bore you, but I would suggest you go to the folder Papers of Interest and read the 2 papers there on the methodology of good modeling practice.